Okay. Okay, we have one actual honest to God viewer, which means we will get started in 1 minute. All right, I'm going to go ahead and get started. Thank you to David for watching live and anyone else who watches this on YouTube. This is a new experiment. This is the first time I'm attempting one of these. So I'm Alex. I am fortunate to have a somewhat eclectic background. At different points, I've been a site reliability engineer, a security engineer, a back-end engineer. I've worked on antitrust litigation. And one of the good things that comes out of having a very eclectic career like that is that you work with lots of smart people and you get to learn from them. And one of the things I have most enjoyed about working with and learning from smart people is the ability to try to synthesize things and take concepts from one person's field and apply them to another. And so that is the basic thesis of what's going to happen here. So today's case in point is, why do vulnerabilities persist? And this is really, for me, going to be at taking stuff I've learned from SREs and applying it to thinking about security. So we're going to start by conducting a pre-mortem, which, if you haven't encountered one before, pre-mortem is like a post-mortem, but in reverse. And so instead of having an actual failure, you hypothesize a failure and then try to imagine why it happened and use that to proactively find what are the things I could have done to be preventing this. So in our case, we're doing a pre-mortem for a SQL injection vulnerability that is exploited in production against us, and we lose integrity and confidentiality, which is to say attacker is able to read and write whatever they want in our database. So how did the SQL injection come to be? Well, if we knew absolutely nothing else about our application, just truly no facts, we might assume it is something like this. That is to say, kind of the platonic ideal of a SQL injection vulnerability, most simple imaginable, just pure string concatenation of some attacker-controlled parameter with a SQL string. And probably by volume, this kind of basic string concatenation is the most common source of SQL injection in the world. And so if this is our hypothesis for how SQL injection might have happened, how can we work backwards to figure out what are the things we could have done to prevent this, and therefore actually do those things to protect ourselves? So with a vulnerability this shallow, probably we can hypothesize that the developers who wrote the code weren't familiar with SQL injection at all, and so maybe some training on common web security vulnerabilities and how to prevent them. And maybe actually some of our developers had familiarity with SQL injection, but we didn't have a code review process. So let's add mandatory pre-merge code review so that we increase the chances a developer who is familiar with SQL injection sees it. And maybe the real problem is that we're manually crafting SQL queries with strings, and we should be using an ORM or a query builder API where users don't construct SQL queries at all. The library generates them, and therefore the library is responsible for properly handling parameters, making sure they're passed to the database safely, and that would also prevent this. Again, given this is an incredibly shallow bug, almost certainly, really 100% certain, it would be catchable with static analysis. And so let's go ahead and add some static analysis to our continuous integration and make sure we fix all of the findings from it. And another option we have available to us is kind of monitoring, looking at a different kind of portion of the spectrum. So successful SQL injection and production almost always involves many failed attempts to exploit the vulnerability, and those failed attempts often produce invalid SQL, which should produce some sort of database error, which is probably in our logs. And if we monitor for invalid SQL queries and alert on those, that gives us maybe a high signal way of knowing if we have an ongoing incident that needs immediate response. And so maybe we would have been able to remediate that before the attacker was able to, say, exfiltrate our database. So we've got a bunch of potential action items, and I think these are all good action items. I'd be remiss if I didn't say that kind of developer training is usually a very weak action item, but with something this kind of shallow, probably it has a place. But probably you can think of a bunch more action items. Maybe the data that was stolen shouldn't have been retained. Maybe the app that was breached didn't need access to the full database. Plenty of other things. Goal of this talk is not to explore all the different ways you might prevent SQL injection. Because after all, this was a contrived example, right? This is kind of the platonic ideal of a bad SQL injection vulnerability that kind of truly should never exist, right? Notwithstanding that, I hypothesize they're pretty common in practice. For our applications, we don't have vulnerabilities this shallow, right? So let's have a slightly more sophisticated pre-mortem. No more kind of clown shoes vulnerabilities. Let's presume we've got developers who are familiar with SQL injection. We have code review. We have an ORM. We've got static analysis. We've got monitoring. We're kind of a normal, company with a bunch of reasonable protections. And yet we're still going to hypothesize a SQL injection vulnerability is exploited in our application, leading to a loss of confidentiality and integrity. How did it happen? So we had all these security controls, but unfortunately the developers didn't use the ORM because they were implementing an analytics query for customer dashboarding, and our ORM doesn't have all the kind of advanced, SQL features we need. It doesn't do window queries, and it was kind of a big query because analytics. So building up the SQL string for it was split across a few functions. That caused our static analysis tool to miss the vulnerability because it only does, function local analysis. And our manual code review missed it for the same reason. Or in the alternative, maybe the static analysis caught it, but our static analysis has so many false positives that we didn't catch this one in triage. And we do log SQL syntax errors to our exception tracking system. Unfortunately, we're not really at exception 0, and so alert fatigue kind of swallowed them up. So notwithstanding all of our good controls, there's what I think is a pretty reasonable scenario. Probably all of the considerations here are things we've seen in real life. So notwithstanding all of those, we did not have enough to prevent our users from getting hurt. And so pretty clearly, we just need we need more controls, right? We need our query builder to be more expressive so we can use it for even for analytics queries. And we need to improve our static analysis to handle non-local control flow, or maybe make it fail closed if it can't prove a SQL query is safe. And we need to prioritize the exceptions in our tracker so that we alert on the really security sensitive ones. And we probably should go and add more penetration testing and get a bug bounty going to get some external researchers to report this stuff before it's really exploited. And we're going to have to hire some more software engineers and security engineers to actually do all this. And probably we can keep going for a while with all of the things we might like to do. And if we do everything we want to, what will happen next? Well, I think three things will be true after we add all of these, reasonable and positive controls. First, we will dramatically reduce the likelihood that SQL injection makes its way into our code base and is successfully exploited against us and our users, right? This stuff will work mostly. Some of the mitigations we've talked about will probably be costly and burdensome to implement, either in developer time, or we'll have to pay money for some external static analysis tool. There'll be a lot of false positives we have to triage. And the third thing I think will probably still be true is some SQL injection will continue to slip through our defenses, and we'll have a risk that it will be exploited against us. And so even if every one of our controls we can imagine gets implemented, there's still a chance of SQL injection. What does that mean? I work on security because I want to prevent people from getting hurt. And that kind of answer of, we can't guarantee that a vulnerability like this won't happen, and really at the limit, preventing SQL injection may be in tension with other things we care about, and thus we can't even have all the controls we'd like. It doesn't sit well with me at all. And an unsatisfactory answer like this requires us to go back and re-review assumptions and maybe find a more fundamental way to attack the problem. Look for creative ways to square the circles. When we identify action items in a pre or post-mortem, I think it's useful to step back and think about where do those action comes from. The easiest thing to do is always simply solve the bug in front of us, literally just fix the bug we have and maybe prevent the exact manifestation from occurring. But there's a saying, generals are always prepared to fight the last war. We don't want to invest tons of effort in preventing literally exactly one type of vulnerability. We want to generalize because bugs rarely recur exactly as we saw them before. We want to find sort of what's the generalization of this? What's the vulnerability class? What's the exploitation method? What's the through line that lets us fix lots of bugs at once? But we also have the constraint, we don't want to be too general. We want, things that you can actually action on, not merely thought experiments. And taking examples and turning them into a cohesive class that can be addressed is one of those skills we all develop as we level up as engineers. So when I step back and I think, why did the SQL injection happen? How did it make its way into production? The answer I come to is it made its way into production because it wasn't secure, but it was functional. The application worked for almost all parameters on the developer's machine. It worked in continuous integration. It worked in QA. It worked with real customers. It worked even though it was insecure. And I think it's a dangerous combination. So here's a table of the basic cross product of is it secure and is it functional? And I think in general, we don't care too much about the right side of the table. We don't care too much about things that don't work because things that don't work don't tend to make their way into production for the most part. All right? When the application just doesn't work, and if it does make its way into production, it's the kind of thing we roll back. So we don't actually care too much about whether something is secure if it's non-functional because, we have lots of the whole development and product team is invested in catching things that don't work. Things that work and are secure, that's what we're trying to enable. But things that work and are insecure, the bottom left corner, those are dangerous because those are the kind of things that make their way into production and can potentially be exploited. Most of security deals with the question of how do we move things from the bottom to the top? How do we take them from insecure to secure? And we talk about things like safe by default APIs or misuse-resistant cryptography as different kind of approaches we can take to take an API from being insecure to secure. Think like a HTML templating language that has auto-escaping on by default. It takes kind of basics outputting of a variable and takes it from an XSX exploit to automatically escape. So going from this code is insecure to secure. And And I think it's also true of many of the controls we thought about in terms of preventing SQL injection, right? That's like the role a query builder plays, taking just a parameters passed to it and making it automatically secure by default. So this is a tried and true approach. It works. Are any of the two concurrent viewers familiar with Diane Vaughan? So Diane Vaughan is a sociologist, and she coined the phrase the normalization of deviance while she was investigating the causes of the Space Shuttle Challenger disaster, which killed all 7 crew members. So the proximate cause of the Challenger disaster is a failure of both the primary and secondary O-rings to seal in the solid rocket booster, that was caused by low overnight temperatures. Diane's research looks at how NASA and its contractors came to launch a space shuttle that was susceptible to that failure mode in that scenario. So, and normalization of deviance is part of the answer. She comes to a big part. So, for her, normalization of deviance refers to the process by which deviant behavior, that is to say, behavior that doesn't conform to the safety rules or procedures, becomes normal over time within an organization. And the path this happens by is remarkably simple. Organizations got some process. Sometimes people forget unintentionally to follow it, and nothing bad happens. And if nobody forces that self-correction, over time, people will learn, both at a conscious and subconscious level, that if a rule isn't actually required to prevent catastrophe, they will learn that the rule is not actually required to prevent catastrophe. After all, if the rule is regularly ignored and catastrophe doesn't happen, then the rule must not be doing much. Very quickly, deviation from this rule becomes the norm, not the exception. It's probably at this point worth the really uncomfortable observation that there are plenty of widely used security practices that if we normalize deviance from them, probably nothing bad would happen. For example, the extremely widely held requirement to rotate one's passwords. For years, this is considered security best practice. It's still widely used, but we know that it adds nothing of value. In fact, we've got research that suggests it's actively harmful to have a password rotation policy requiring timely rotation in the absence of compromised passwords. So a thing a reasonable person might see is, well, if they ignore the, we'll call it voluntary requests to rotate their password, nothing bad will happen. Maybe all security policies have this property that if you ignore them, nothing bad happens. So it's like a pretty uncomfortable thought and a pretty good reason for us to care a lot about whether the things we ask of people are actually contributing, and if they were ignored, would anything bad happen? Would users realize? But in many safety critical contexts, particularly in kind of non-software engineering, the thing you're concerned with is accidents. This is kind of the context of research that comes out of the shuttle, lots of other kind of engineering contexts we look to learn about safety engineering. And accidents happen, we'll say, with kind of like a random distribution, with maybe probability 1 over n, and n can be pretty big, so that gives you lots of times to normalize deviance. Like what temperature the shuttle launches at is, nobody is controlling the weather, right? That's kind of a random stochastic process. But in computer security, we're really concerned with intentional malfeasance, right? We have attackers who are trying to break our defenses, break into our systems. And that means in the inverse, right? If we don't have an attacker, we might never discover vulnerabilities, right? Kind of in our idealized case, the attacker who finds our vulnerabilities is actually ourselves, or like a red team or a bug bounty we have. But it's really important to observe, if we never look for a vulnerability, it tends not to be found, right? Because vulnerabilities occur kind of in the edge cases. In our original SQL injection, if ID is always supposed to be numeric, it will never happen in the regular course of our application. It will only happen when somebody starts throwing other values, say with quotes or kind of other pieces of SQL syntax in. That's the only time we'll actually discover a vulnerability. And this is basically the recipe for normalizing deviance, right? Because this means code can exist for arbitrarily long periods of time without forcing any sort of self-correction on us. And it gives us that functional but insecure recipe. And it, teaches developers, this is a perfectly safe habit. It teaches security teams, maybe that something doesn't exist, no problems exist, right? It's very easy to treat no news as good news, even when we know the only way there'll be news is if we go looking for vulnerabilities. So I think a tool we need to add to our toolkit is, instead of looking for ways to move from the bottom half to the top half, that is, instead of just looking for ways to go from insecure to secure, we need to think about ways to go from the bottom left to the bottom right. How do we take things that are insecure and functional and render them non-functional instead? After all, my basic thesis is that if at a basic level something doesn't work, the fact that it's insecure will not be relevant because it'll never make its way into production. It means developers will never learn bad habits. It means we won't need extra static analysis to attempt to catch it. Lots of our controls fall by the wayside because if we have the property of when a developer tries to do something that would be insecure, it simply doesn't function. And so this is kind of basic thesis of the talk, is we need to add this tool to our toolkit. How can we design and build systems that resist allowing normalization of deviance, and how can we kind of make this functional but insecure box impossible to reach? So going back to kind of our root SQL injection, why is it possible to have a SQL query that functions but it's insecure, has this basic SQL injection vulnerability? So my basic thesis is kind of, instead of, or maybe in addition to, looking for ways to break SQL injection, we need to break vulnerable code even in the absence of injection. And why does vulnerable code work? Because SQL allows non-parameterized queries at all, ever, for kind of any value. So let's take kind of 3 examples of SQL queries. The first one we have is kind of the string concatenation, or in this case, I've migrated to the Python f-string syntax, but it's still its base string interpolation. So the first one is vulnerable. Second one is obviously not a vulnerable query. It's just there's a fixed ID there. And the third one is kind of the best practice. In the example, I've got fixed ID, but you could equally imagine that second parameter being, like request.gets ID, and we know it would still be safe because it's kind of parameterized in that way. And the important observation is that from the perspective of the database, the first 2 queries look the same. The string interpolation in the first query happens in Python or PHP or whatever language, and so the database doesn't know if string interpolation happened or not. It doesn't know if you have kind of the literal in the second query or the interpolation in the first one. And so any thesis of how we prevent the first one, it also necessarily has to involve breaking the second one. And so what does that mean? Well, we need to remove literals from SQL entirely. No more literal strings. Because without literals, no interpolation-based scheme will ever work. If you want to query by a value, the only way to have that work will for it to be a parameter, and thus protected from SQL injection. Pretty obviously, this is like a fundamental and radical change to SQL, and like to a first approximation, every application that uses it, right? Because literals aren't only used in the case of injection. They're also used for constants that pose no risk, like our second query here. But if we want to take this approach to breaking SQL injection, the constants have to go because the database can't tell the difference at all. It's important caveat to note is this does not actually truly prevent against all SQL injection. If you have a interpolation for a column name or table name, those aren't literals. It's just you just kind of write the table name there or the column name there. So we still need some SQL injection controls to protect against this case. But if we dramatically reduce the attack surface of our database, we can look at very different cost benefits for what kind of controls we need. And in my experience, at least, SQL injection kind of in the place of a literal is by far more common than in the place of column or table name. And so, rolling this out in practice, if, we're the Postgres core developers or something, you could imagine kind of an incremental path where we start by adding like a pragma that you can turn on a per session basis. Hey, don't allow literals on this connection. Then we update all of the popular web frameworks and database libraries to turn that on by default. And then in 5 years, Postgres changes the default. You can kind of imagine that incremental rollout. But of course, the point of this talk is not just to think about SQL. SQL injection is not the only vulnerability type out there. And I think this framework of normalization of deviance and trying to identify why vulnerable code worked at all and how we can prevent it from working is applicable to a bunch of vulnerability classes. And so it's a valuable tool in our toolkit. So if you're listening to this talk, it's quite likely you know that I'm a person who thinks memory safety at a programming language level is super important, and that kind of belief comes from the same basic place. Memory unsafe programming languages allow deviance to normalize because you can forget to add a bounds check, and that will work perfectly well forever, right until somebody actually passes a value that is out of bounds. And so we want to look for opportunities to use techniques like this in more places. So I want to go through another example. So this is kind of a canonical example of a use after free vulnerability in C code, like our original SQL injection. It's so trivial. Obviously, no one writes code like this. Also, equally obviously, there's lots of use after free in the world. So, like, some variant on this pattern exists everywhere. And like with SQL injection, hopefully most engineering teams that use C have some combination of static analysis and dynamic analysis and training and red teaming, etc. And we know that's also insufficient in the real world, although it does help. So using kind of this framework of functional but insecure, we can also think about approaches to make this code as written safe. So we might introduce a garbage collector that turns free into a no-op and keeps the allocation alive as long as there's a reference to it. And this works, and it's kind of the canonical, right? Unsafe to safe, right? Bottom to top approach. And you see this in things like the Bohm garbage collector, or even Chrome has taken an approach kind of similar to this with the thing they have called Miracle Pointer. And Rust takes the inverse approach and breaks this code, right? The type system doesn't allow you to safely represent code with use after free vulnerabilities like this. So this is kind of a rough Rust equivalent. We create a box, which is roughly equivalent to malloc, and we drop it. It's kind of like free, and then we try to use it afterwards, and then we get a compilation error because there's a move, and you try to use the value after it was moved, where move means free. And so this would prevent normalization of deviance, right? You can't successfully write code with safe Rust that has kind of use of a value after it has been dropped. And so you'll never kind of unintentionally learn habits of programming that involve use after freeze. So I hope it's clear that for some types of security challenges, adding this as an additional tool to our toolkit of making vulnerable systems non-functional may be a better approach than trying to make them secure because it might be more tractable and it may be more comprehensive, might have less failure modes. I want to talk about another reason that I also think this approach is important. Building really large numbers of controls into the development workflow is just an inevitable burden on a team. Everything takes time to run, and it has a bunch of findings. You got to prioritize them, and you got to adjudicate false positives, and you need some process for when the security team disagrees with the engineering team on if something's a false positive, and you got last-minute findings that need to be resolved before release. And rendering a system non-functional when it's insecure can ironically reduce the burden, right? It's not breaking things just intuitively seems like it should be more burdensome, but it's the ultimate shift left in terms of giving actionable feedback to a developer immediately, not in CI or nightly or before release, but as they're writing the code. And systems that resist normalizing deviance ultimately require less supervision because there's less gray zone, less space to argue or dispute about is something a false positive, is it really safe? We get much closer to if it works, it is safe. And that can be really freeing in terms of the need to oversee software development. So that's the basic thesis. Kind of things I hope folks take away from this are that this kind of functional insecure is this danger zone that is really a key part of how any vulnerability comes to make its way into production, right? Occasionally we see vulnerabilities in things that never worked. You see those occasionally, but mostly you see vulnerabilities in things that do work. And so in general, we want to think about designing systems that avoid normalizing deviance. And in particular, we want to look for ways to make insecure code non-functional. This will not work for every scenario. For example, I spent a lot of time trying to think, well, how can we make command injection impossible via this? And I couldn't find a way to it. So this is not the be-all, end-all of security, but it is a useful extra toolkit. And I think it's useful, importantly, to have a vocabulary for this type of approach, because this is an approach that's real, right? Rust has been doing its thing for well over a decade, and I think having a vocabulary for how we can make insecure systems non-functional is valuable, and it's a useful extra tool for security engineers. I think thinking kind of in terms of Diane Vaughan's Challenger research is a really valuable thing. So I encourage folks to read Diane Vaughan's book on the Challenger disaster. And yeah, that is that's what I got. I think we have one viewer, so I'll hang out for a minute if there's questions. Otherwise, thanks for listening. And whether or not anyone views this, I will probably do a few more on some other similar topics. Cheers.